We are looking at 2001 Electricity and Magnetism, question number 2. This is a somewhat strange question because they kind of set it up in a kind of interesting way with this graph here. But what we have is a potential difference, so a voltage graph as a function of time. And we have been hired to determine the internal resistance of an 8 microfarad capacitor for an electronic company manufacturer. We know that ideal caps have zero internal, or an infinite internal resistance, but the material in reality has a very small but non-zero conductivity. We can't connect the caps to an ohm meter because their resistance is too large for the ohm meter to measure. Therefore, we need to charge the capacitor and then discharge it across something and measure the potential difference across the capacitor every 20 minutes with an ideal voltmeter obtained in the graph above. So what we're doing, since we don't have to discharge across anything because it has an internal resistance, but what we're asked to do is determine the internal resistance of the cap. Now for all of these things here, there's actually a few ways to do this. This is the easiest one, and by far it is the easiest. The first thing we could recognize is for an RC system, which this is what it is, it's a cap with an internal resistance, we know the time constant tau is equal to RC. This is the time for a half-life. So if you remember your nuclear physics or whatever, this is the amount of time for a half-life. So if we want to take a look at this, the time for a half-life here, let's see. It's like just under 60 minutes because it starts at 10, and that would mean, well, really, 40 would take us to 5. That's a half-life. What are other half-lives here? Where's 2.5? 5 to 2.5 is at 70. So that's only 30. And then 1.25 is like here. That's much longer. Let's see. What do we want to take for that half-life then? 7 is about here at 20. 3.5 is about 60. So our half-life, I would say, is somewhere between, it's somewhere between 40 to 60 minutes. It's somewhere in that ballpark. Okay? Because I want these values in seconds, I don't want to do 40 times 60 in my head. I'm just going to take the 60 value. I'm just going to take it the high end of things because this from here to here is 60 as is. And then 1.25 to 0.75, it's 130 to 1. That's like about here. That's about 60 as well. So I'm going to just take it as 60. What I can say then is that 60 times 60 is 3,600 seconds is our half-life. That has to equal to the internal resistance multiplied by the capacitance, which is just 8 times 10 to the micro minus 6 farads. And that's all I have to do there. Maybe this number is a little different based on what you determined for the half-life, but whatever you say with the half-life there, depending on what you've found in that graph, that's good enough. You have to use that graph for some sort of estimation there, so that's what we have. And because we're only measuring that potential difference every 20 minutes, 40 to 60 does seem somewhat accurate there based on our curve. So let's see. If we take 3,600 divided by 8 times 10 to the minus 6, oh, that's annoying. Let's see. We get an R value of 3600 divided by 8 times 10 to the minus 6. Oh, 4.5 something. 4.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th. And that's resistance, so it's in ohms. Woo! For part B, the capacitor can be approximated as a parallel plate capacitor separated by a 0.1 millimeter thick dielectric with a K value of 5.6. So what we have to remember now is that a capacitance of a capacitor can be given by the dielectric K times epsilon naught, the cross-sectional area of those plates, and then divided by some d. That's the distance between the plates there. So for this, we just have to enter in values, and then figure out what A is. So here, let's solve this for A first. This will give us that A equals C times D over cap epsilon, which is going to be 8 times 10 to the minus 6th. 0.1 millimeters is, let's see, that's times 10 to the minus 3, but it's 0.1, so 1 times 10 to the minus 4 meters divided by 5.6, and then epsilon naught, that's a lookup number, but it is 8.85 times 10 to the minus 12. If we run all of those numbers together, oh boy, that's a lot of numbers. 8 times 10 to the minus 6 times 1 times 10 to the minus 4 divided by 5.6 divided by 8.85 times 10 to the minus 12. I got about 16.14. Let's just say 16. So 16, and my units were in meters, and because it's an area, it's in meters squared. Okay. Now we have to determine the resistivity of the dielectric. Whew. Okay, well, I know that resistance is equal to rho resistivity times the length over an area. And in this case, we know that, let's solve for resistivity real quick. Rho is going to equal to RA over L. And in this case, we actually know all these values. We know R. R is just whatever we got from part A. So for us, that is 4.5 times 10 to the 8th. Maybe your number's a little different, but be consistent. Your cross-sectional area is what we found in part B here. That's our 16 or 16.14, whatever you have. I'm just going to use 16 because I'm lazy. And then the length here, well, normally when we talk about wires, we talk about some extruded length. Our length here is actually the 0.1 millimeter thickness. That's all the length that we have, so to speak, within this dielectric. So that's just going to be 1 times 10 to the minus 4 meters again. And, oh boy, 4.5 times 10 to the 8th times 16 divided by 1 times 10 to the minus 4. We're going to get 7.2 times 10 to the 13th. And our units for that are going to be ohms. And that will be what? An ohm meter. Because these are ohms, these are meters squared, and this is a meter. So ohm meters. Cool. That is our resistivity. And then we're almost done with this problem. This has been a quick one. Kind of strange, but a quick one. Determine the magnitude of the charge leaving the positive plate of the capacitor in the first 100 minutes. Woo! Amount of charge leaving that plate. Well, like the problems before this, there are a few ways to do this one. And what we can actually do here is we can just say that the change in the charge is equal to the capacitance by the change in voltage. And in the first 100 minutes here, let's see, our voltage goes down to about 2 from a value of 10. So we can say here that our voltage difference is about 8 volts. So our change in charge is just going to be the capacitance, which we have is 8 times 10 to the minus 6 farads. And then our difference there of 8 volts, right? So we're going to get, well, 8 times 8 is 64. And then times 10 to the minus 6 is micro. And charges has to be in coulombs. So there it is. Boom, done. If you wanted to, you could use a like RC discharge equation there. CV times the quantity 1 minus e to the minus t over RC, and then like calculate it that way. Looking at that amount of time. You could also do this. Another neat way you could do it is, since this is a potential difference, you could figure out what a current time graph would look like and then take the area of it. But by far, like, this is the easiest way to do it. You didn't have to do any calculus with it. You just got the values straight up because you knew an initial and starting point. So kind of a quick problem, but a little bit of a fun one, a little bit of something different. Kind of a different RC graph, or a different RC problem that we are used to seeing. A lot of options for you there. But yeah, with that, this problem is finished. Take it easy. Have a good one. Go check out the other RC problems. Bleedoo!